Hello everyone, this is our next video on the series of electric potential and capacitance. For older videos you can refer to the right pinned video, right? So let's recap a bit about what we discussed in the last lecture and then we'll continue with the new topics, right? So we discussed what is a capacitor, right? Capacitor is nothing but a system of conductors, system of two conductors separated by some dielectric or insulator, right? Separated by some dielectric. And this system is capable to store charge, right? So let's say this has plus charges around, this has minus charges around, and hence there is an electric field in between, right? So I have indicated electric field as uniform electric fields. And if you see practically these are not uniform electric field. There will be some kind of stringing effects and things. But what we assume ideally is the area, let's say area of one plate is A and distance between the plates is D. So we assume this area is very greater than the distance, or let's say distance square, right? So we assume that these plates are infinitely long in the area, like the cross section is very large when it's compared to the distance, and hence we can assume these fields as uniform electric fields, right? So this system of conductors, which is a capacitor, is capable to store charge, and hence it has bonded electric field in between, right? It has bonded electric field in between, right? Now let's move to the next topic. Energy stored in capacitor, right? So we just discussed what is a capacitor, right? Let's start with an uncharged kind of capacitor, right? Initially let's start with let's say this is a capacitor with no charge on it, right? Now if I need to store charge on this capacitor, right? If I need to store charge on this particular capacitor, right? Let's say this is a capacitor which is neutral as of now. There is no charge on it, on the plates. And if I need to charge this particular capacitor, we discussed that we will connect it to some supply, some battery, and then say this is a battery or a cell. This is the higher potential terminal and this is lower potential terminal. So this is positive plate which is connected to higher potential terminal. This is negative plate, it is connected to lower potential terminal, right? And net potential V is nothing but difference of those potential, right? Now if I need to charge this capacitor, we know that electron is responsible for any conduction, right? So this cell will supply electrons, right? This will supply electron will accumulate on the negative plate first, and it gets some charge, some negative charge, and this negative charge is responsible to develop some positive charge over the positive plate. How it develops, it is through a induction process, right? You see there is no contact in between the plates, but still this negative plate is able to transfer charge to the positive plate. So this is induction kind of process, right? But you see this positive plate is connected to higher potential, right? And you need to supply charge from a lower potential to a higher potential. Naturally charge will never flow from lower to higher potential. You always need to do work to make charge flow from lower to higher potential, right? Because every time naturally charge flow from higher to lower potential, right? So to supply charge from negative to positive plate, you need to do some amount of extra work, some amount of external work, and that work will get stored as potential energy in the capacitor, right? That work will get stored as potential energy, but we will call this as electrostatic energy in case of a capacitor, right? So now capacitor definition will change, like capacitor is a system which is capable to store charges, which is capable to store bonded electric field, and which is capable to hold electrostatic energy embedded into them, right? And since we know that electrostatic forces are conservative forces, right? They are conservative forces, so work done will get stored as some kind of energy, right? And since it is electrostatic force, the energy and any parameters will only depend on the initial and final, right? It won't depend on the path, how capacitor has attained charge. the energy is not bothered about the path, right? It is only dependent on the initial and the final state of the capacitor, right? So let's derive the expression of energy stored in the capacitor. Right. Okay. So let's say this is a capacitor, right? This is a capacitor. And at any instant, this negative plate is holding some charge minus q dash, and this positive plate is holding some charge plus q dash, right? So what is the potential at this particular state? Potential will be nothing but q dash by she, right? The potential difference between the plates is nothing but q dash by she. This is how we know that expression of capacitor is q equal to cv, right? Now what I want to do is I need to transfer some delta q charge, let's say delta q dash charge, from negative to positive plate, right? I need to transfer delta q charge from negative to positive plate, right? So we need to do some external work here. So work is nothing but work is equal to potential into charge, right? Work is nothing but potential into charge. So to transfer this small amount of charge, which is let's say dq dash, I need to do dw amount of work, and potential is q dash by c, right? If I need to calculate network, so network is the integration of this. Network is integration of dw with respect to integration of dq dash, right? Now I am assuming that at initial, let's say at time equal to 0, my initial charge was 0, right? Or at time equal to t, my charge was let's say q, right? So let's put the limit. When work done was 0, it was w, charge was 0, it was q. So w becomes 1 by c into q square by 2, which is nothing but q square by 2c, which is nothing but q square by 2c. This work done gets stored as electrostatic energy in capacitor. This work done gets stored as electrostatic potential energy in capacitor, right? And that energy will be given by u equal to q square by 2c. And this can has multiple forms. Can I write it like this? If I substitute q equal to cv, it becomes cv square by 2c. It can also become half cv square, right? It can also become half cv square. And I can also write it like this. Like if I take it again, q square by 2c, I can segregate it like this, q by c into q. This becomes half into v into q, right? So there can be multiple ways to write it. But if I segregate and write everything together, if I collate and write everything together, it becomes u equal to q square by 2c equal to half cv square, and also equal to half into v into q. Clear? And this is in potential energy, and this will be in joules. And capacitor as a device is capable to store this much amount of potential energy in it, right? And hence it is capable to do multiple more electric charge and discharge, right? So this energy will be used when capacitor discharges, right? When capacitor is charged, it holds this energy, but when we need to use this energy, we need to connect that capacitor to any external device, and capacitor will give its energy to that device, and it will discharge, right? Right. Now let's discuss one more term, which is energy density of a capacitor, right? And we will talk this explicitly for a parallel plate capacitor, right? Parallel plate capacitor. So the topic is energy density in a parallel plate capacitor. Parallel plate capacitor. So before deriving the expression, let's understand what is energy density, right? Let's say this is a parallel plate capacitor. This is a parallel plate capacitor. the area is A, the distance between the plates are D, plus Q and minus Q are my charges, and sigma is the charge density, right? Surface charge density. So if I need to calculate volume of this region, the volume of this region, I can simply calculate and say that it is nothing but area of cross section into distance, which is A into D, right? A into D is the volume. So energy per unit volume is energy density, right? So U, which is energy density, is nothing but energy stored per unit volume, right? So if U is capital U is my energy stored and volume is V is my volume, so sm small u is energy density. The unit will be joule per meter cube, right? So in this case, this will be U by A into D for this particular problem, right? Now let's derive the expression for energy density in a parallel plate capacitor. We know that U is nothing but Q square by 2C, right? Q square by 2C. Now, what is the relation between sigma Q and A? So sigma is nothing but Q by A, right? Sigma is nothing but Q by A. So Q becomes what? Q becomes sigma A. Q becomes sigma A. Now, capacitance of a parallel plate capacitor is given by epsilon A by D, epsilon naught A by D for if air is the dielectric. So if I put sigma and if I put Q and C from these expressions to this particular relation, let's put it. So it becomes what? Sigma A square by epsilon naught A into D. So this becomes sigma square A square D by 2 epsilon naught A. This becomes sigma square AD by 2 epsilon naught, right? This is energy, right? Now if I take U by AD, this becomes what? Sigma square by 2 epsilon naught. Sigma square by 2 epsilon naught. And this U by AD is nothing but U, which is energy density. We just calculated that capital U by AD is nothing but energy density, which is energy per unit volume, and it is given by sigma square by 2 epsilon naught, right? So this is the expression to calculate energy density in a parallel plate capacitor, right? Right. So next topic is parallel plate capacitor with a dielectric, right? We already discussed how dielectric affects the property of capacitance, right? How it affects the way the capacitor stores energy, right? And how we can choose a value of capacitance based on dielectric as well, right? Now let's discuss it specifically for parallel plate capacitor. So let's say this is a parallel plate capacitor, right? This is a parallel plate capacitor. This has a dielectric in between. This has a dielectric in between. This is a dielectric, right? Let's say distance between the plates is D. Distance between the plates is D, right? And let's say charges on the capacitor is plus Q on this plate, minus Q on this plate, right? Plus Q on this, minus Q on this, right? Now, since we have a dielectric in between the capacitors, the dielectrics will be subjected to the electric field which is present in between the capacitor plates, right? You know, there is an electric field in between capacitor plates indicated by E, right? So this dielectric will be subjected to that electric field, and hence the dielectric will polarize, right? And if it polarizes, it will develop some charge, right? There will be a development of charge in dielectrics as well. If I zoom dielectric here and if I make it here, so dielectric will have charges as something in this manner, negative towards the positive side of positive plate, and it gets positive charge towards the negative plate, right? You know, unlike charges attract each other. So let's say this dielectric gets minus QP and plus QP charges, right, along its surfaces, right? So now this again, this also acts like a separation of charge now, and this will be responsible for one more electric field here. So because of this dielectric, there is one more electric field here, which is EP, right? Because of this dielectric, there is one more electric field here, which is nothing but EP, right? Now, let's derive what is value of this EP and what is the value of these terms QP, which are the polarized charges in the dielectric, right? Right. So this dielectric has developed some polarized charges because of the electric field of this capacitor. Now we will derive two quantities here. How the capacitance of this parallel plate capacitor is varying when I have placed a dielectric inside it. Let's say K is the dielectric constant of the dielectric, right? It is the dielectric constant. You know, dielectric constant is nothing but permittivity of medium by permittivity of free space or vacuum, right? Okay. So capacitance is given by what? For a parallel plate capacitor, capacitance is epsilon naught A by D. But this is when the dielectric is air or vacuum. So this is C naught. Let's say this is C naught. Now, C is my new capacitance when I have placed a dielectric. It becomes what? Epsilon A by D. It becomes epsilon A by D. If I take a ratio of C by C naught, it becomes what? Epsilon by epsilon naught, which is nothing but K. So C is nothing but K into K times C naught. K times C naught. So you see, the capacitance after inserting dielectric has become K times the capacitance when dielectric was air or vacuum. So after inserting a dielectric, we can actually increase the capacitance of a capacitor because K is always greater than 1, right? Now let's see the induced charges. You see the induced charges has developed, right, on the dielectric. So what are value of these induced polarized charges, right? Okay. So let me draw it diagrammatically again, how it looks like, to just be clear, more clear. So this is a parallel plate capacitor and this is dielectric in between, right? This was a parallel plate capacitor, this is dielectric in between. So this has a charge plus Q, this has a charge minus Q, this dielectric has a charge minus QP and this has a charge plus QP, which is because of the polarization, because of a electric field inside the capacitor, right? Now what is electric field in between plates of a capacitor? Electric field in between plates of a capacitor is nothing but sigma by epsilon naught, right? Electric field in between plates of a capacitor is sigma by epsilon naught. But this is the case when my medium is air or vacuum, right? In case my medium is dielectric, which has a dielectric constant K, my electric field will become sigma by epsilon in between the plates of a capacitor. It becomes sigma epsilon, which is my equation 1, right? Now analytically, if I calculate electric field because of the induced charges, you see there are two electric fields existing here. One is because of the capacitor plates, which is in this direction. One is because of the dielectric induced charges, which is in this direction. So if I call this as E and this as EP, net electric field is nothing but E minus EP. If I call this as net electric field, this is E minus EP, right? This is also my net electric field. So again, applying this same expression, it becomes sigma by epsilon naught and this becomes sigma P by epsilon naught, right? This becomes sigma by epsilon naught, this becomes sigma P by epsilon naught, and net electric field becomes sigma minus sigma P by epsilon naught, right? If I write in terms of charge, we can also write in terms of charge as well. This becomes nothing but Q minus QP by A epsilon naught, right? And this becomes what? Q by A epsilon, right, in terms of charge. So let's say this is my equation 2. Clear? So now you see equations 1 and 2. LHS is nothing but net electric field, right? So LHS is equal, RHS will be equal. So if I equate it, it becomes Q by A epsilon will be equal to Q minus QP by A epsilon naught, right? So AA will cancel out. So epsilon naught by epsilon equal to Q minus QP by Q, right? So if I take this LHS, it becomes 1 minus QP by Q is nothing. This epsilon naught by epsilon is 1 by dielectric constant, because K is epsilon by epsilon naught. So if you find QP from here, which is charge on this dielectric, right, amount of induced charge on this dielectric, it becomes QP becomes Q into 1 minus 1 by K, right. Using this expression, you can also find the charge induced on these dielectrics, right. Okay, let's solve problem on these topics, right. So let's solve a problem on this system of capacitor which we have discussed, right. So this is a capacitor, right. You see these blue lines indicates the plates of a capacitor. You see this is a parallel plate capacitor, and there is a dielectric inserted in between these plates of a capacitor. You see this dielectric is not covering all the region of the capacitor. It is only covering till a thickness T, right. It is not covering the whole distance between the capacitors. So for distance T, D minus T, this region is still air. This region is still air, which has K equal to 1, dielectric constant as 1, and this region of dielectric has dielectric constant given as K, right. We need to find the capacitance of this whole system, right. We need to find capacitance of this whole system. Now you see, if I try to distribute this particular problem, this is, if you see a top-down approach, you see this is like a two capacitors in series, right. This is like two capacitors in series. One capacitor which has air as a dielectric, and other capacitor which has a dielectric placed, a slab placed in between it, right. So if I break this particular problem, this looks like this particular situation where I have one capacitor C1 which has capacitance C1, and this has dielectric as air, and then I have another capacitance C2 which is another capacitor which has dielectric constant as K in between them. And if I need to find the net capacitance in series, we know for series it is C1 into C2 by C1 plus C2, right. You can easily calculate using how we discuss for series combination, right. So if I am able to find C1, if I am able to find C2, I can easily find what is C net, right. Okay, let's try to find C1, right. Let's try to find C1. So capacitance of a parallel plate capacitor is given by what? It is given by epsilon naught A by D, right. But general, if you see, if I take for general capacitors which does not fall in this air or vacuum dielectric, so it becomes epsilon A by D, right. And K is nothing but epsilon by epsilon naught. Epsilon is K epsilon naught from this. So if I place, this becomes K epsilon naught A by D. So using this formula, let's find C1 and C2 here. Let's find C1 and C2 here. So what we need dielectric constant, we need area, and we need distance between the plates, right. So if you see this particular diagram, C1 will be nothing but K epsilon naught A by D, right. Let me put this D as D and this A as something A dash, right. So K is 1 for C naught, epsilon naught is same, area is again, cross section is again same, and distance for C1 is D minus T, right. So C1 is epsilon naught A by D minus T, right. What about C2? C2 is again same expression. For C2, K is given as K only, epsilon naught is epsilon naught, area will be again same, and distance for C2 is T. So for this capacitor system, the capacitance is K epsilon naught A by T. Now net capacitance of the system will be nothing but C1 into C2 by C1 plus C2. You can place the values and find what is the net capacitance of a system, right. Okay, yeah, right. So next topic for us is RC circuit and charging of RC circuit, right. So this is a kind of a very application oriented topic, because RC circuits are circuits which are used in a lot of electronic circuits for different applications, right. This RC circuit, for example, can use like a filter. It can be used as to modify voltage from one form to another, so it can be used as a voltage converter and many things. If you go ahead in this field and you will study this RC circuit has lot of applications, right? So how capacitor plays a role in this RC circuit and how it charges and discharges, we will study that here, right? So let me draw a RC circuit here. So RC circuit consists of a resistor and a capacitor connected in series, right? A RC circuit consists of a resistor and a capacitor connected in series. And if I connect this to a system of battery, let's say V, this battery will charge this particular capacitor, right? Initially I'm considering this capacitor is discharged, right? Before going into how it is charging and things like that, let's understand this resistor and capacitor, they are passive elements, right? So in electric circuits there are two types of elements. One is active elements, right, which are our sources which gives us energy, like cell, battery, they are active elements. And then there are passive elements which are resistors and capacitor, because they dissipate that energy, they consume that energy, so they are passive elements, right? As simple as that. So now initially when capacitor is discharged, right, and there is no supply connected to it, the charges on the plate of capacitor is 0, right? When I connect a potential V or a battery with potential V to this series circuit, a current will be induced, right? So capacitor has a device to oppose change in voltage around it, right? Capacitor will oppose sudden change in voltage around it, right? Right. So initially at t equal to 0, when my capacitor is discharged, there is no charge on capacitor, there is no current in this circuit, right? And we know expression for capacitor is Q equal to CV, right? So initially when my charge is 0 on this capacitor, the potential across the plates is also 0, and capacitor will act like a short circuit, right? Short circuit means it will not disturb this flow of current initially, right? So this is like a this kind of circuit, right? A short circuit condition, and it's like nothing is connected in between. So if by Ohm's law, if you calculate current at time equal to 0 in this circuit, at time equal to 0, the current in this circuit will be what? V by R, which is called I naught, and this current is called charging current. Charging current. So using this current, there will be a development of charges and hence energy in the capacitor, right? And we will see how voltage across capacitor will vary with respect to time during its charging cycle, right? Okay. Now, this is a kind of a bit advanced topic. So if you are just working on for boards and things, you can neglect this, but yeah, just for knowledge. So if current flow in this circuit in this direction, this will develop a polarity like this, right? Plus minus, and this will develop a polarity like this again, plus minus, right? Now there are two voltages here, right? One which is induced across this resistor VR, one which is induced across this capacitor VC, correct? Now let's calculate what are these voltages. So voltage across resistor by Ohm's law will be I into R. If I use simple Ohm's law, V is proportional to I, V equal to IR. Voltage across capacitor is nothing but Q by V, right? Voltage across capacitor is Q by V. This is my V is my voltage of battery, which is called EMF, which we will study later on what is EMF. But as of now, you see this is a constant voltage source which is supplying current, right? So V, if you see the net expression, this V, the voltage of this battery will be equal to voltage of this across this resistor and voltage across this capacitor, right? Because this is what is creating potential difference across these two passive components, right? So this V will be equal to I into R plus Q by V, I into R plus Q by V, right? Now we don't have any common components here, right? Let's convert current into charge form. What is current? Current by definition is flow of charge, rate of flow of charge, right? So current is nothing but current is rate of flow of charge. So this VR can be also written as dq by dt into r, right? So can I write it like this? V equal to dq by dt into r plus q by v, right? dq by dt into r plus q by v, right? So if I take dq by dt now, dq by dt into r, this becomes v minus q. Oh, sorry, this is not v, this is q by c, right? Q by c, v minus q by c. So now dq by dt is 1 by r into v minus q by c, right? dq by dt is nothing but 1 by r into v minus qc. Can I write it like this? Minus of 1 by r into q minus cv by c, right? Now let me take the values here. Let me do a, because I need to integrate to get the charge. It becomes q minus cv, and this becomes minus dt by rc, right? Now let's integrate these quantities. At time equal to 0, my charge was 0. At time equal to t, my charge was q. Clear? Let's integrate and see what value of charge we get. So integration will be nothing but ln of q minus cv, 0 to q, and this will give me minus t by rc, right? Let's put the limit. Ln of q minus cv minus ln of cv, this is nothing but minus of minus t by rc, right? Because this is modulus, right? So this becomes ln of q by cv minus 1 equal to minus t by rc. So q by cv minus 1, if I take an anti-log here, it becomes e to the power minus t by rc, right? So if you calculate, you will get q equal to cv into 1 minus e to the power minus t by rc, right? It becomes q equal to cv into 1 minus e to the power minus t by rc, right? So we discussed when a capacitor is initially discharged and it is connected to a battery or potential V in series with a resistor, the charge develops on the capacitor using this relation, which is cv into 1 minus e to the power minus t by rc, right? What about voltage on the capacitor? Voltage is what? Q by V, right? Q by C, sorry. So it becomes V into 1 minus e to the power minus t by rc. If I plot graphically, right? If I plot graphically, let's say charge and time. At time equal to 0, you take this equation, first equation. At time equal to 0, my charge is 0. It is discharged totally, right? And if you see this charge, slowly it will increase, right? Slowly it will increase, right? And at time equal to, at a very high time, you see that it will become something like cv, right? Which is like infinite time, right? So this is how charge varies with respect to time for a capacitor. This is a kind of exponential function, right? And not a linear relation. So capacitor is not a linear device like a resistor. Resistor, if you see, things are kind of linear, right? Even if you plot voltage with respect to time, the relation will be again same, right? Relation will be again same. There is a parameter called R into C, right? R into C. This parameter RC is called as time constant of RC circuit, right? So this R into C, which is value of resistance multiplied by value of capacitance, it is called as time constant of the RC circuit. And this is the rate, this basically tells me the rate by which a RC circuit is charging or discharging, right? If I have a high time constant, the charging will be faster. right? If it is lower, it will be again vice versa, right? So if you see in this graph, at time equal to RC, at t equal to RC, the capacitor will be charged around something like 37% of its total voltage, right? 37% of V, it will be charged, right? And generally it is said and proved that a capacitor needs net of 5 time constants to get fully charged, right? It needs 5 time constant to get fully charged, right? Okay. And after a capacitor gets fully charged, it behaves like an insulator, right? Means it will no more allow any further charge to come around it, and it will stop the flow of current across it, right? So we will discuss more on this and what is discharging of RC circuit in the next series, next video. Yeah, till then, thanks.